And ladies and gentlemen, after a long time away, we are back recording. Now I know this cartoon probably is certainly more appropriate for Valentine's Day, but thought we would do this one in honor of Miss Gossett and her Justin Bieber obsession. Strange as she is and strange as he is, but if you want to keep reading it, I'll move this box out of the way. You can pause the video and read, otherwise I'm going on. Now, today we want to revisit parametric functions. This is obviously a topic that we have discussed in pre-cal, and we've even mentioned in calculus a little bit thus far. But we want to look specifically at how calculus does play into parametric functions. And we will just review parametric curves in a plane. We'll talk about derivatives of parametric, slope and concavity. We'll then discuss arc length, and then we'll end up with a topic called cycloids. Alright? Let's begin. Example 1, reviewing some parametric curves. Just a quick review of how we graph with parametrics. Our job is to sketch the graph of x equals cosine t, y equals sine t. Now, ladies and gentlemen, remember your t values need to be 0. Most of them will start at 0 and will go positive. They don't have to go up by a specific number. Now, I picked these numbers. Obviously, if you look at them, hopefully you recognize them from the unit circle, which are going to make doing this problem a lot easier because we do know those values from the unit circle. Now, to get each x value, like x is 1 here, I take the t value 0 and I plug it in for t right here. Cosine of 0 is 1. To get the y values, I take that same t value and I plug it in here. Sine of 0 is 0. And we continue on. Cosine of pi over 6. Cosine of pi over 6 is radical 3 over 2, which is 0.9 approximately. Sine of pi over 6 from the unit circle is 1/2. Continuing on, cosine of pi over 4, radical 2 over 2, or 0.7. Sine of pi over 4 is the same thing. Cosine of pi over 3 is 1/2. Sine of pi over 3, radical 3 over 2, which again is 0.9. Now, I'm going to go on and go through this. If you want to pause the video and finish completing the tables, you can. But from here on out, it's just the same numbers repeated as is in the unit circle, but of course with sign changes. So if you want to pause it now and complete it yourself, you can. Otherwise, I'm going to skip on through them. And of course, this is taking a while, so entertain yourself in whatever boring and yet appropriate way you see necessary. And almost there, almost there. There are all of our numbers. Now our job is to take each of these numbers and make a coordinate point. So for instance, the first point we plot will be 1, 0. Then we'll plot the point 0, 0.9, 0.5, 0.7, 0.7, and so on, and so on. And when you do that, you get this sketch right here. We start at the first one, which was 1, 0 here. And then it moved around, and it moved around, and moved around. Now, I do want to remind you, although my graph does not show it because Geometry Sketchpad would not, but remember that you should have arrows. So, for instance, I would have an arrow right here, if you see the right here. I'd have an arrow right there, and it would be pointing in the upper left direction because that was the way that the graph was moving. You know, we moved around, 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 and we went around. So you should have arrows moving this in a counterclockwise direction. Okay, and that is our graph. Now the next part said, eliminate the parameter to find an equation that relates x to y. So this is where, ladies and gentlemen, back up just a second, this is where we would figure out a way to combine our x function and our y function into just one function without the t. And there were usually a lot of ways that we would do this. Sometimes we would solve one equation for t. Other times, when trig was involved, we would use identities. And of course, the identity we would use that you saw just a moment ago is the Pythagorean identity. Cosine squared plus sine squared equals 1. Now, if I take sine, which is y, and plug that in, and cosine, which is x, and plug that in, I have that. Cosine was x, x squared. Sine was y, y squared. And now this makes perfect sense because x squared plus y squared is a circle, centered at 0. With a radius, when we look over here, a radius of 1, and that's exactly what we've sketched. Alright. Now, again, I want you to do the same thing. If you want to pause the video now and fill in all these numbers, I'm just going to skip through them because I'm sure you can take these numbers from the unit circle it really won't be very hard at all. But I'm going to go ahead and skip through these, so if you want to fill in the table yourself, pause the video now. Again, just to make sure you understand, for instance, if to do pi over 3, I would plug pi over 3 in for the t right here to get the x value, cosine of pi over 3, get that times 3. Get the y value, I'd plug it in for sine of t, multiply it by 2. Now, you're going to sketch all these on a graph if you would. And again, if you want to do that now, pause the video. Otherwise, I'm going to go on and let you look at the graph. And our graph looks like this. Of course, this is an ellipse. If you remember ellipses, as a major axis, it looks like of 6 from here to here. A minor axis of 4, still centered at 0, 0. Now, what about eliminating the parameter? Well, I'm going to again start with that same Pythagorean identity, sine squared plus cosine squared equals 1. And I'm going to plug it in, but before I can plug them in, notice I need to solve. So, for instance, before I don't just plug in x for cosine, I first of all need to solve for cosine, so I divide by 3. I need to first solve for sine, so I divide by 2. So instead of just x squared, it's x over 3 squared, and instead of 2 squared, instead of y squared, it's y over 2 squared. And when you square that out, x squared over 9, y squared over 4, and there's our answer. Now, if you remember from pre-cal when we did conic sections, again, we're centered at 0, 0 on our ellipse right there. Take the square root of 9 is 3, so I move left and right 3 in each direction. Take the square root of 4, I move up 2, down 2 in each direction. So it works out perfectly. Alright, let's do another problem like the ones we have been doing. Now this one's not quite sine and cosine. It's not the trig stuff. So you see, I've changed the parameters. No longer am I using numbers on the unit circle, but I did pick just easy numbers. Deal with these numbers from 0 to 4. Now you have noticed, I hope, on each of these, it has given me an interval in which to work this. Now that being said, ladies and gentlemen, I'm going to plug 0 in for here and for here, and when I do that, I get 0 and -2. I plug in 0.5 here and here, that gives me 0.7 and -1.5. And you can continue to plug in these numbers here into the t values here and fill in the table. So if you want to do it yourself, pause the video now. Otherwise, I'm going to flip on through it. Alright, there we are. Now, just as we have done before, take yourself a coordinate plane and make a sketch, ladies and gentlemen, of these points. Pause the video now if you want to do that by hand. And we end up with this graph here. You see it. Our first point starting was at 0, -2, which is here. So again, I'm going to make my arrows. I'm going to make them so that they start here and they point in the direction that you see it moving on the screen. I really wish the Geometry Sketchpad would let me do that, but it won't let me put arrows on the graph. So make sure you've got arrows moving in this left to right direction on the graph. Now, what about eliminating the parameter? Well, I'm going to start out by solving this one for t. Now, no trig identities on this one because there's no trig. So I square both sides. T equals x squared. I will then take that x squared and I will plug it in down here for t, and you see that's our equation, which makes perfect sense. I mean, look at this. It is a parabola. So you see this part of the parabola right here, and it has been shifted down 2, so -2. Now, it's only part of a parabola, but it is still a parabola. Now let's bring calculus in. How do we find the derivative of a differential formula? Well, remember the differential formula gives you a y equals and an x equals. So to find dy dx, I consider this. dy dx is the same thing as dy dt over dx dt, because if you think about algebra, the dt's would cancel out. Well, what does dy dt represent? That simply represents the derivative of the y equation. So, on one of them, remember we had y equals sine of t. You would just take the derivative of sine t. dx dt likewise represents the derivative of just the x equation. So now let's consider this problem. Consider the curve x equals t squared minus 5 and y equals 2 sine t. We're going to A, sketch the graph. So when I'm done with the explanation here, you can pause the video and do that. I'm going to just kind of skip through it. B, I'm saying to indicate which direction is traced. B, find the highest point on the curve. We'll use derivatives for that. And then C, find all the points of inflection on the curve. So we'll use the derivative for that. So I'm going to, at this time, fill out my table. Again, I'm going back to trig. Even though this one was not trig related here, this one was. So I use some of the values on the unit circle from 0 to pi. So pause the video now if you want to fill out the table yourself. And there are our numbers. Now, you can make this sketch, and it looks like this. And you see, it's kind of sloppy, but I tried to draw an arrow in there so you could see which direction it's moving. Now, the next thing it wanted us to do is it wanted us to find the highest point on the curve. Well, now this is not as bad as it would sound. The highest point on the curve only is concerned with the y value. Don't really consider the x just yet. Now we'll find the x here when we're done, but the highest curve really only is here. So what I'm wanting is what is the maximum value of this. And if you remember maximums and minimums, they are all about the derivative. So I take the derivative, dy dt is 2 cosine t. And then of course you remember you take your derivative and you set it equal to 0, and then you solve for t. So I divide both sides by 2, I do the arc cosine. Where's cosine equal to 0? At pi over 2. Now also at 3 pi over 2, but remember our interval here is 0 to pi. So what does that tell me? Well, that tells me that if I take this pi over 2, if I want to find the highest point on the graph, which looks to me to be about right here, I take that pi over 2 and I plug it in up here for the x formula, and I plug it in right here for the y formula, and we get that. Or if you can go back and look at your table, we already had pi over 2 plugged in, and it was negative 2.52. So that's where the highest point would be. Now, part C, find all points of inflection. Ladies and gentlemen, this is going to be a bigger problem. Points of inflection would consider both the x and the y. And not only do I need to do the first derivative, but of course, you know, points of inflection describe concavity, so I need the second derivative also. Let's begin with the first derivative. The first derivative, again, it's the derivative of the y equation over the derivative of the x. So that would be the derivative of the y would be 2 cosine, and derivative of the x equation would be 2t. Not bad, but the second derivative now we have a fraction, so we are going to have to do our quotient rule. So we'll start out with bottom times derivative of the top minus top times the derivative of the bottom over the bottom squared. Or, I'm sorry, should have thought to simplify first. But now we do what I was saying, and we do the quotient rule, and we have this. Obviously, simplifying the 2's would have been a much smarter thing to do. I forgot about that. But still, bottom derivative of the top minus top derivative of the bottom over the bottom squared. Now, again, this, ladies and gentlemen, if I may pause for just a second and explain one other thing, this is the second derivative of this part. But now, when you're doing the second derivative here, it's a little different than just taking the derivative of this. The second derivative, by definition, is the derivative of the first, which we just did, over dx dt. Now, there's a variety of reasons why, and I'll be happy to explain that in class if you want. But when you're doing the second derivative with parametrics, you'll take the derivative of what you just got for the first derivative, which we did by the quotient rule, and you'll put that over dx dt, which is the derivative of the x, right here. Alright? Now, that being said, let's see what we can do to simplify this. Of course, this would be negative t sine t. That would become minus cosine t, and all of this would become 2t cubed, like so. Now, this is our second derivative. Remember, concavity changes inflection points are where concavity changes, and that's where the second derivative is 0. So I need to set this equal to 0. Of course, in setting it equal to 0, I know that the bottom does nothing. It's simply just gone, because 0 on top is what gives me 0. But ladies and gentlemen, at this point I see we're about out of our time on the first one. It's nearly 15 minutes, so I'm going to stop now, and we'll finish this problem on the next video.